Stationary wave. Stationary wave is a periodic disturbance which forms waves that's non-progressive and does not have energy transmission. So let's take a look at an example. Example of stationary wave: if you take a stretch string on both sides and you vibrate and oscillate them, you end up producing a stationary wave moving from the full line to the dotted line. The stretch string will first vibrate along the normal line, and thereafter it will move to the red one, and thereafter you will actually end up as the purple line, which at the instant moment all the vertical displacement is 0. Then it will actually then in the segment here it will be vertically displaced upwards, and you will follow the blue line, eventually going to the dotted line, and thereafter the cycle repeats. So let's take a look at some of the terms that we typically use to describe a wave. We still continue to use the word amplitude to describe the maximum displacement. We also use the wavelength, so the definition of wavelength remains the same for stationary wave, which is no different as progressive wave. The only two terms that's new that we'll be using is one is antinode. Antinode is when the displacement is maximum. And typically in the case of a progressive transverse wave, we will call them actually the crest or trough. The next term that we look at is your node. Nodes occurs when the displacement is 0. Earlier, when we described how the stretch string has oscillated, we will know that at the nodes, the displacement remains 0 all the times. Aside from stretch string, we can also form stationary wave in a closed or open pipe. At the closed end, the air particle which is in contact with the base of the container is not able to vibrate in this direction. So therefore, because of that, the air particle will remain at its equilibrium position all the time, and therefore this is actually the node. That is that the displacement of the air particle in this case is 0. On the contrary, at the opening here, the air particles is free to vibrate at both sides, and hence because of that, it is actually the antinode. So if you now take a look at the open pipe, you will find that at both ends, the air particles is free to vibrate freely. So therefore, both sides is actually the antinode. So let's take a look at how we can calculate the wavelength for stationary waves. So in the case of this stationary wave, if the stretch string has if the length of the stretch string is L, then in this case there will be 1 wavelength, 2 wavelength, 3 wavelength, 3.5 wavelength. So 7/2 wavelength is actually equal to L. So we can work out that L to be equal to 2L/7. Let's take a look at the closed pipe. In the closed pipe here, we actually have if the length of the pipe is L, then in this case, 1/4 L lambda/4 is actually equal to L, because from an antinode to a node is actually 1/4 of a wavelength. So your wavelength is equal to 4L. Finally, we take a look at the closed pipe. In the closed pipe, the length is L. Between antinode and antinode, it will actually be half a wavelength. So half a wavelength is now equal to L. So your wavelength is equal to 2L. So let us now take a look at the conditions for occurrence of a stationary waves. First, you need to create waves. You need to create two waves. You need to create waves that travel in opposite direction but at the same speed. Waves need to have the same amplitude, so that when they needs to have the same magnitude, and finally the wave need to have the same frequency. So these are the conditions for stationary wave to be produced. Let's now take a look at the differences between stationary and progressive wave. The first is the amplitude. For stationary waves, the amplitude of each particle varies. The particles at the antinode will have a maximum amplitude, while the particle at the node will have 0 amplitude all the time. The rest of the other particles will have amplitude greater than 0 but less than the maximum amplitude. While in the case of progressive wave, all the particles have the same amplitude. Next, we look at phase difference. So all the particles between the nodes will have the same phase, because you can see they will start off at the red line and they will all move downwards towards the blue, then the light blue, then the brown, then the yellow, and they all move in the same direction. So the particles are in the same phase between the nodes. At the adjacent segment, you will find that while the particles at this segment is moving downwards, the particles at the adjacent segment are all moving upwards. The particles in this segment will have a phase difference of 180 degrees or pi radian. While in the case of progressive wave, the phase difference will be calculated based on this formula, depending on where the position of the particle is vis-a-vis that of the wavelength. Energy. In stationary wave, there's no translation of energy associated with the wave, while in the case of progressive wave, the energy translation is in the direction of travel of the wave. Frequency. The particles on the stationary wave all vibrate in the same frequency, with the exception of the particle at the nodes, because at the nodes, the particles do not vibrate and the frequency is 0. While in the case of progressive wave, all the particles will vibrate in the same frequency. To determine the wavelength of stationary wave, we know that the distance between adjacent nodes or adjacent antinode is half the wavelength. While in the case of progressive wave, wavelength is the distance between adjacent crests or adjacent troughs. Displacement. Displacement of particles in the case of stationary and progressive wave are all the same. In this case, the particles return to the equilibrium position twice with every complete oscillation or period. Obviously, this similarity does not apply to particles along the node. Finally, if you look at the velocity of the wave, the stationary wave does not have a velocity in the direction of its travel. However, the particles will still exhibit vertical velocity in accordance to simple harmonic motion, which is similar in the case to progressive waves. The only difference is that in the progressive wave, the velocity of the wave is in the direction of the energy transmission. Finally, in the exam, if you're asked primarily to state the differences between the progressive and stationary wave, typically we will pen the difference in terms of its amplitude, its phase, and its energy transmission. Finally, we'll take a look at now how we can measure a stationary waves for sound using a signal generator that produces a waves that gets reflected by a metal reflector, in the process creating a stationary waves between the signal generator and the metal reflector. And thereafter, we will use a microphone which is connected to a cathode ray oscilloscope, where the microphone is able to sense the variation in pressure and pipes the information to the cathode ray oscilloscope. When the microphone registers the largest amplitude on the CRO, when the pressure is the highest, is where it is actually the node. Most people would have thought that it is the antinode. That is not correct, because if you can recall at rarefaction and compression, you will notice that in the case of compression, all the particles are moving towards the point of the compression, and the displacement of the particle at the point of compression is 0. Similarly, at rarefaction, all the particles will be moving away from the point of rarefaction. The particle at the particle at the point of rarefaction has a displacement of 0. So hence, we have a simple way to help ourselves remember that the displacement node is the pressure node, so we call it D and A. So D and A. So when you manage to pick up 2 maximum pressure using the microphone, the distance that's traveled by the microphone is actually between 2 nodes, so if you let the distance be L, L will therefore be equal to half lambda. Thereafter, we'll be able to find the wavelength of the stationary wave. Finally, bear in mind that the pressure node is the displacement antinode. So at the antinode, the pressure actually remains unchanged at average atmospheric pressure. Finally, for stationary waves, let's take a look at the possibilities. The first possibility is actually between the stretch spring, as mentioned, as described earlier. So we will always kick off by drawing the largest possible stationary wave that could be produced. That is how you're able to work out your fundamental frequency. To do that, we'll typically have 2 nodes, and in this case, we just have an antinode. So from there, we know that if the length of the stretch string is L, then wavelength is half. So half the wavelength is equal to L. So your fundamental frequency is C equal to 2 over L. Now we'll move off to the next harmonic. To create the first harmonic, we'll be adding one more segment, or we'll be adding another node to node. So in this case, previously, there's only one segment, okay, between two nodes. Now, in the case, if you take a look at the blue line, you have one segment, you have another segment, okay? So with that, the wavelength now is directly equal to L, and you can see that F1 is now equal to C over L, but it's important to take note it's actually 2C divided by 2L. You can see it is actually a multiple of your fundamental frequency. Next, we go to the second harmonic. In the second harmonic, we'll add in another one more segment. So in this case, previously with two segments, now we add one more. All right, if you take a look at the red line. So from there, we know that this is 1.5 wavelength. So 1.5 wavelength is equal to L. So from there, we work out that the F2 is now 3C divided by 2L. So hence, in conclusion, we can safely conclude to say that once we work out the fundamental frequencies, there's rest of the other frequencies that will generate the stationary waves in the various form that we have sketched will be actually multiples of the fundamental frequency. Now let's take a look at the instance whereby both ends are actually open pipe. So if you take a pipe with both sides that's open, then both sides will actually be the antinode. And you can see in the same vein, when we are trying to work out the fundamental frequency, we will make sure we draw the largest possible stationary wave. In this case, it will be antinode here and antinode here. There will be a node here. So let's take a look at the black line. Okay, so if you do that, you end up with the same expression. Now we'll go on to now take a look at the first harmonic. In this case itself, we'll take a look at the blue line. So similarly, in the same vein, we're trying to add one more segment. So you can see that the extra segment that we added is here. Okay, if you follow the blue line. All right. So originally, in the fundamental frequency is this. Now in the first harmonic, we add one more segment. So you end up with the blue line, with the blue sketches. Okay. So because of that, you will still end up with the same expression for this, because now the wavelength is exactly equal to the length of the pipe. Finally, if we now want to take a look at the second harmonics for the open pipe, then what we do is that we now add another one more segment. So you have one segment here, two segments, and then you have the ends that actually meet the requirement that the both sides needs to be antinode. So from this, we also end up with exactly the same expression. So in summary, it means that in questions that where both ends are nodes or both ends are antinode, they will all form stationary wave at frequency, which is a multiple of the fundamental frequency. Now, finally, let's take a look at an example where you have a closed pipe on one side and an open pipe on the other. So in the same vein, to work out the fundamental frequency, we'll be looking at the black line. So we'll be working out we'll be sketching the largest possible stationary waves. So in this case, this will be the stationary waves that you're looking at. So therefore, it's actually a quarter wavelength. So a quarter wavelength is equal to L, F0 is equal to C over 4L. Okay. Finally, so in the first harmonic, we will then actually add one more segment. So you follow the blue line. Okay. And in this case, 3/4 lambda is equal to L, and we can work out that F1 is 3C over 4L. You can see that in this case, there are actually odd number of the fundamental frequencies. Okay. Finally, if you take a look at the red one, so we add one more segment. So originally there was only, in the first harmonic, there's one more segment here. Then in the second harmonic, we have one segment here, another segment here. Then this is actually the antinode. So in this case, 5 lambda over 4 is equal to L. And from there, we can work out that the F2 is actually 5C over 4L. So in summary, when you have one end that's node and one end that's antinode, the conclusion that you get is that you get stationary waves. In this case, you've produced stationary waves with the fundamental frequencies and the various odd number of the fundamental frequencies, which means that in short, in the case of this, if a fundamental frequency is 100 Hertz, then the next frequency that will produce a stationary wave will be 300 Hertz, 500 Hertz, 700 Hertz, 900 Hertz, so on and so forth. While in these two cases itself, if the fundamental frequency is 100 Hertz, then you will be getting your next stationary waves or first harmonic at 200 Hertz, 300 Hertz, 400 Hertz, 500 Hertz, so on and so forth.